Okay, so the next section that we're going to discuss for population ecology is we're going to talk a bit about how populations grow. And that's going to be one part. And then we're also going to talk a little bit about the different ways that populations sort of can exist, what their lifespans are like, okay? And that's something we call life history. So it'll make more sense once what that is once we get into it, okay? But before we go there, population growth. So there are two mathematical models that describe population growth. And something important to realize is these are both mathematical models. So populations don't follow these exactly, because nothing in nature is precise like that, at least nothing that's alive. But they kind of represent two patterns of how populations grow, okay? And so the first pattern is called exponential growth. And so I know you all are at all different places in your math, okay? So for some of you, you're like, oh, I know exactly what that means. And some of you are not so much, and that's okay. Essentially what exponential growth means is that a population grows kind of slowly at first, but it quickly becomes very rapid and is extremely rapid, okay? As an example of exponential growth, what they're showing you here is bacteria. The reason that they've chosen bacteria is that some bacteria, not all, but some, have a reproduction rate of 20 minutes. So what that means is that every 20 minutes, a bacterial cell reproduces and makes a new bacterial cell, okay? All right, so let's just follow the numbers here, shall we? All right, so you start off with one lonely bacterium, okay? After 20 minutes, you have two, right? Since both of those then reproduce, then you have 4. 20 minutes later, you have 8, okay? It's called exponential because here's the math that describes that process, okay? So they're showing you the first, 1, 2, 3, 4, 5, 6 reproductive cycles, right? So we go from 1 to 64. And then they start leaving out, some of the details just so that you can see how it quickly picks up, okay? So from 1 cell to 64 after 2 hours, but that becomes 512 after 3 hours. That becomes over 4,000 after 4 hours. And by the time we get to 12 hours, that's 68, almost 69 billion. Okay, this is why you don't want to eat leftovers that have been sitting around on the counter for too long, too many hours, because bacteria grow fast. Yeah, that's why. Okay, exponential growth is characterized by a J-shaped curve, right? So you'll notice that this curve here looks kind of like the letter J, okay? Now, an important thing to realize about exponential growth is that exponential growth sort of implies that there is no limit to resources, okay? So in reality, okay, this little flask here, right, is meant to show a flask that has nutrient broth. That's what we call the water and, liquid and whatever that we're trying to grow, liquid food, right, that we're trying to grow the bacteria in. Right? So that's what that's supposed to represent. So there will come a time when the bacteria will have used up all the resources in that flask, right? They will not have any more space. They'll run out of food. They'll run out of water, right? Resources are limited in reality. So eventually the population will crash, okay? So keep that in mind. Okay, so one way that populations grow is through exponential growth. There's another little diagram, shows you time. Okay. A lot of other organisms experience something called logistic growth. Logistic growth is sort of similar to exponential growth in the beginning. So I can't cover it with my hand. You can't see that I'm trying to cover that up, right? So if you look at the beginning of this graph, right, it starts off with that kind of J shape, right? It's, you know, sort of, and then it kind of zooms up, but eventually it kind of levels off, right? And then the population is sort of maintained at a certain size, right? So in this last one, let's go back to this, right? So x-axis was the time, right? So start to, you know, forever. And then this is the size of the population, so the number of cells, okay? In this one, instead of showing you minutes, they're showing you years because they're tracking a population of fur seals in this example, right? And so they're looking at this population of fur seals. Specifically, they're counting the male breeding male fur seals in thousands, right? So at what year was this? If we're looking, these look like they're units of 5. So in 1910, the population was barely over 1,000 of breeding male fur seals, okay? And at first, the population rose pretty rapidly, right? But by the time you get to around to 1935, right? By the time we get to around there, things are starting to slow down, right? And starting to level off, okay? That leveling off is referred to as the carrying capacity. Oh, my computer is hot today. I wouldn't be surprised if it starts getting weird on me. Okay, let's keep our fingers crossed because I hate making videos 14 times. So carrying capacity, right, is like right there, okay? And essentially what the carrying capacity is it represents how large the population size, how large the population can get without using up all of its resources, right? So the carrying capacity is the population size that the environment and the resources can support, okay? Population density that resources, running out of space, can support. Okay, so the idea being that in the beginning, right, the population grows rapidly until there's starting to be some pressure, right? So, you know, there's not enough food for more than a certain number of fur seals. There's not enough space for more than a certain number, right? And so that certain number is the carrying capacity, okay? And once they start to have some pressure from limited resources, right, the population growth slows way down and often stops, right? It kind of stops and then is maintained, right? So this is like the population density that is maintained, okay? All right. So here's another graph of that, right? So at first when the population size is really small, growth is practically the same as exponential in the beginning, right? It's very J-shaped at first, but then it ultimately kind of starts to slow down, right? And it becomes more of an S shape until the population reaches its carrying capacity, right? And so then the growth rate is 0. It doesn't grow anymore, right? And the population size stays pretty constant. Now, when you look at graphs of real organisms, there's often a little bit of kind of back and forth. It's not like straight, like, oh, there are exactly, you know, 9,072 breeding male fur seals exactly, and that's exactly how many there will be until the end of time, right? It's like you have a few too many and then some die and it goes down and then so it, you know, it kind of, it's a wiggly flat line. Okay, all right, so that's logistic growth. And so so here's a side-by-side comparison between an animal that experiences, what was the J-shaped one called? What was that called again? Exponential growth. And an animal that experiences logistic growth. Very good. Okay. So side by side, right? Exponential logistic. There you go. All right. Now, it's really easy to kind of, if we just left the conversation here, it'd be really easy to think, well, exponential growth must not happen that often because it's just not that realistic. I mean, how many situations do you have where there are unlimited resources, right? Is that ever a thing? Does that ever exist? And the answer is no, right? There is always a limit to resources, okay? But many species still have that type of growth because in some cases, their population growth, the speed at which their population grows, is controlled by something else. Okay, so that's what we're going to be looking at next. Okay, so those are the two growth models, exponential and logistic. So J-shaped versus S-shaped graphs. Okay. All right, so what are we talking about here? So when we talk about the size of a population, we can talk about different factors that impact or limit that population size. And those factors can be density dependent or they can be density independent, okay? So let's talk about density dependent first because that's here, okay? And then we'll talk about density independent. All right, so the illustration that was chosen for this is, you know, a couple of wolves fighting over some dead critter. I don't know, buffalo, something. It looks awfully hairy. Anyway, whatever. Okay, so what are some examples of density dependent factors? So first of all, what does that mean? That means that the impact of these different factors is determined by how dense the population is. Okay, so our first example is food supply. Whether or not there is enough food for everyone depends on how many everyones there are, right? So whether or not there's enough food for your wolf pack, right, depends on how many wolves are in the pack, right? So it's density dependent, right? The effect of food supply on that population is determined by the density of the population. Okay, so the size of the population. Having enough habitat for living and breeding, so actual like physical space, right, is another thing that's density dependent, right? Is there enough space for everyone? Well, it depends on how many everyones there are. Yeah, does that make sense? I hope it does. Okay. This is something that we're feeling right now. We are feeling this, okay? Another density dependent factor is parasite and disease risk. So we're gonna talk a little bit more about parasites next week. So for now, don't worry so much about that. But disease risk, this is perfect, okay? So why is it in the time of COVID that they are telling us not to gather in groups of more than 10 people? Why are they telling us that? Because the more closely packed a large number of people are, the more likely we are to transmit infectious diseases to one another. Okay? That's why people get sick in the winter, by the way, right? That's why people get colds in the winter. It's not as much about the weather, right? Grandma tells you to put a hat on when you go outside because you lose all this heat through your head. And that, I mean, that's true, right? But the reason that you get colds is not because of the cold. It's not because you got cold. The reason that people get colds is because when it's cold outside, we spend more time indoors with other people. So we are more densely packed, right? Density dependent factor. Okay. Also, risk of predation depends on how dense you are, right? And that it varies in different ways depending on if we're talking about like schooling behavior in fish or other things. Okay. But those are all examples of things where the impact of that factor, right? The impact of food supply on population growth, the impact on habitat availability on population growth depends on how big, how dense the population is, okay? So those are density dependent factors. These are the kinds of things that are responsible for keeping a population in a logistic growth kind of situation, right? So the density dependent factors are the things that keep us at carrying capacity. And I say us in the general sense. I'm definitely not talking about humans. I'm talking about fur seals. Okay. All right. And sea lions. Cute. Anyway. Okay. How do density dependent factors control population sizes? Sometimes it's a matter of reducing the number of offspring that are born or hatched or produced, right? So here's a little graph. And so all of these come from actual studies, right? And I'm not super concerned that you can like interpret them in tremendous amount of detail, but you know, it's just worth looking at. Okay, so there was a study in, what year was that? 1992, that was looking at song sparrow populations, right? And they discovered that as the density of the population increased, so as the number of females increased, the number of offspring that each female would produce, so the number of eggs that she would lay, would go down. So birth rates go down when density is high, okay? Because she doesn't have as much access to food. And if she can't have as much access to food, she's not going to be able to make as many eggs. Yeah? Or she makes a bunch of eggs, but if she doesn't have enough food to feed her babies, then they're not going to make it to adulthood. They die. So that's the other side. Right? So density dependent factors often lower birth rates. That's what we're looking at here. And also can increase death rates. Okay, so declining reproductive success. Oh, what are you doing? Declining reproductive success, right? Or increasing death rate, right? So the more dense these, kelp perch is a type of fish. Okay, so these little fish, as their density, right, goes up, their death rates also go up. So their risk of dying goes up as there are more and more of them. Okay, density dependent factors, right? So in general, the larger the population size, the lower the birth rates. That's what this graph is telling you. Okay, so as population size gets bigger, right, birth rates get lower, and so the graph goes like that. Okay, all right. If that's what a density dependent factor is, think about what a density independent factor must be. I promise I won't drink so much on camera when it cools down. Okay, so density independent means the impact of that factor has no effect, or I shouldn't say has no effect. It doesn't matter how big or small the population it is. The density of a population doesn't determine the impact of the factor that we're talking about. So in this example, they're showing you natural disasters, right? Fires, floods, earthquakes, okay? But even normal weather patterns can be a density independent factor, okay? So in this particular example, it's like, it doesn't matter how big or small the population of deer are. If there's a forest fire, the population is going to shrink. The population of deer is going to shrink. And it didn't matter how big or small the deer population was before that happened, right? Hurricanes would be another example. So a lot of times bad luck events, what they're calling it here, or natural disasters are density independent. But like I said, even just normal weather changes are density independent. Okay, so let's look at one of those. All right, so this little crew, there's a different example in your book, but it's the same idea. The one in your book is about butterflies. This one is about aphids, okay? So aphids are these, they're actually kind of cute little bugs, assuming that they're not eating your roses. And aphids are interesting little insects. What they do is they what they eat, the way they make their living, is they suck the sugary sap out of plants. Okay. And so plants are not generally super stoked when they are infested with aphids, because the aphids bite little holes into them and suck out all their sugar and their water. And so the plant kind of suffers. Depending on how healthy the plant is, sometimes they can, struggle through and they're okay, but other times not so much. Okay. Aphids have a very dependable population growth pattern. Okay. So in the spring, right here, we're looking at time. Yeah. Ooh, why does it keep doing that? In the spring, right, we're looking at time. When it starts warming up and the plants are starting to really, get growing, a lot of the like soft annual plants start to grow. The aphid population starts to grow exponentially, right? And the reason that it's growing exponentially is because as those plants are growing, it is seemingly an unlimited supply of food. The weather is great, there's plenty of food, life is good for an aphid, right? So exponential growth, exponential growth, exponential growth. Aphids never get to the point where they reach a carrying capacity though, because around midsummer or so, it gets too hot and they start to die off just because the weather is different, right? Just because it's super hot, they die, right? Also, it means that the plants are starting to struggle a little bit when it's super hot. So, you have this really rapid decline, but it doesn't matter how big or how small the aphid population is. The reason there's a rapid decline is because the weather changed, right? And so that's a density independent factor, because the size of the aphid population has nothing to do with the fact that they decline. It's just because it got too hot for them and they died. Okay, so population goes down, and then over the cold winter months, there's a few around, but their population's real low. Okay, so many times density independent factors have an impact on population growth before density dependent factors can. I'll say that one more time and then just like chew on that for a second. Okay, many times density independent factors have an impact or have an effect on population growth rates before density dependent factors have a chance to. Okay, so I'm gonna let you think about that. Try to see if you can think of another example, even if it's something made up, right? See if you can sort of imagine a situation where that would be true. Okay, all right. Some populations, and now we're starting to border on community ecology a little bit, which I said we're not going to talk about until next week. So I'm not going to get into this too much, but some populations exhibit cycles as a result of their interactions with other organisms. Okay, so like I said, this is really kind of community ecology, but that's okay. So what you're looking at here in this diagram is we're looking at a graph of the population of two species. So this little cute white bunny is called a snowshoe hare, right? And so that's the blue line, right? And this super adorable little kitty cat with the stump tail is a lynx, okay? And so their line is represented in red, okay? So let's look at what's happening here. So I'm just gonna pick one to look at, and then we'll, kind of flip back and forth, okay? So in 1850, the population of snowshoe hares was hopping, right? They were growing, okay? They were on the upswing, right? Looks like exponential growth to me. Okay, all right. Part of what might play a role in that is the fact that at the same time, lynx populations were going down. So not as many of the snowshoe hares were getting eaten. So their population went up, okay? Then their population got kind of, got pretty high. Well, then the lynx population started going up, because now the lynx, he wants to disembowel that adorable little bunny. Just so you know, just saying. Okay. So that lynx wants to eat that cute little bunny, right? And so if there's a bunch of bunnies, tromping around, then guess what's going to happen with our lynx friend there, right? He's going to have a better chance of catching a bunny. He's going to have a better chance of having more babies, right? Because he's got more food. So the lynx population goes up. Well, what's going to happen if there's more predators? So more predators here. So what's going to happen to our hare population? It's going to go down, right? Because now there's more predator. Now all of a sudden there's more lynx there. They're going to eat them, right? So they die. And then their population goes down. And then what's going to happen to the lynx population? Now they have less bunnies to eat. You see where this is going, right? So there's a lot of situations where population growth tends to cycle, and it's usually the impact of another species that's kind of causing that cycling, or sometimes it's like seasonal cycling, like weather kinds of stuff, okay? Or seasonal changes or whatever, all right? Okay. Some population, why do we care about, so let's just kind of talk about why do we care about population growth. The biggest reason why we care about I shouldn't say it that way. One of the most practical reasons, how about that, why we care about population growth is when we're thinking about organisms that supply us with some sort of good or service that we enjoy. Okay, so this is a picture of a fish, specifically it's a codfish. And what we're looking at here is we are looking at the population. Instead of population, we're looking at yield. So we're looking at how many fish in metric tons fishermen are able to catch in these different years of this particular type of cod in this particular place. Right. And so, okay, in the 60s, right, they're catching 500,000 metric tons. All right. Well, something happened in the late 60s, and it looks like fishermen started catching a lot more. Yeah. So better fishing techniques. Right. I don't know. Right. Maybe they're catching, maybe more people decided to become fishermen. It's like, oh, that's lucrative. Let's go do that. I don't know. Okay. So instead of catching 500, it's up to about 800. Okay. Well, part of the problem with this is if you have too much, if you take too many fish out of the ocean, then that makes it so that there are fewer fish in the ocean. And if there are fewer fish in the ocean, how easy is it going to be for a boy fish and a girl fish to find each other? It's going to be a lot harder, right? Yeah. So if the population gets below a certain size, sometimes what happens is the population crashes, right? And so you see how after that short period of really, really high yield of taking lots and lots of fish, it went down, right? And it went down, and went down, and went down, and it was pretty low, right? And then it looked like it was starting to recover, and then boom. Okay. So why do these kinds of things happen? Well, in this particular case, since this is a human-caused activity, right? It has to do with, not being very good managers of resources and knowing how many to take and all of that. Okay, so we're going to talk about this more when we talk about human impacts. Okay, so we're going to come back to this, right? But understanding population growth, appreciating how populations grow, appreciating what factors affect population growth is really important for maintaining healthy populations. Okay. Okay. The next thing we're going to talk about in this video is something called a survivorship curve. Before we do that, I just want to show you this one thing really quickly. We are not going to be using any life tables because, quite frankly, they're actually really confusing to use. It takes a lot of time to figure out like how to read them and how to do the stuff in them. So we're not going to get into this too heavy. If after this semester you decided, Man, that ecology stuff, that sounds really fun. There's lots of good math in ecology. I want to do that for a living. Come back and see me in the BioMajor series, and we can talk about life tables then. Okay. But essentially what a life table is it's actually a tool. Interestingly enough, it actually wasn't developed by ecologists. It's a tool that was actually developed for insurance companies. Okay. So think about, imagine you are a life insurance company. So what does a life insurance company do? They sell insurance to people where the eventual outcome of that is that the person gets paid when they die. Now, usually it's not the person that's actually dead that gets paid, it's their beneficiaries. Okay. So in order for insurance companies to make money, they charge people different rates depending on the likelihood that they're going to have to pay out, right? So you might have noticed if you watch a lot of TV, crappy TV. Nowadays, who does that though? Because we have Netflix now, but whatever. Back in the day, there were all these really lame ads on TV for life insurance for babies, and it was super cheap. And it's like, well, duh, of course life insurance is super cheap for babies, because most young children in the US anyway, right, have a very high likelihood of surviving childhood, right? So if you're paying, $20 a month or whatever it is for life insurance for a baby, that's basically pure profit for the life insurance company, because the chance that they're going to have to pay you anything for that baby dying is like super low. Okay, just practically speaking. All right. How much life insurance, how much do you think life insurance costs for people that are 95 years old? Either a crap ton of money or if it doesn't cost that much, the insurance companies will just say, yeah, you're too high risk, we're not going to insure you at all, right? Because if you're 95, your chance of dying is a lot higher, right, than if you're 2. Okay, so how do insurance companies keep track of that? How do they know that? They developed something called a life table. And a life table is a way of basically quantifying exactly like what is the chance of surviving a certain age. Okay, so this is for US population, and this is kind of old data, it's from 2008, but whatever, it doesn't matter, it hasn't changed that much. Okay, the idea is in the life table is children from the age of 0 to 10 have a 99.2%. So this is a proportion rather than a percent. So essentially what this means is 1 means everyone survives. 0 means no one survives. Okay, so 99.2% chance of surviving to reach the age of 10. Okay, your odds get even better if you make it to 10, because then between 10 and 20, you have a 99.6% chance of surviving. Goes down a little bit to 99% if you're in your 20s, and then 98.7% if you're in your 30s, 97% if you're in your 40s, still in the 90s in your 50s, but by the time you get to 60, it's going down to 87. By the time you get to 70, you only have a 72% chance of surviving. By the time you're over 80, you only have a 40% chance of surviving. Why did it go to 0? What does that mean? Well, since this interval doesn't have an end, it doesn't say 90 to 100, it just says everybody 90 and above. Because we are not immortal, everybody in that interval eventually dies, right? Because they didn't put an end to the interval. So that's why it's 0. Okay. So in doing this, life insurance companies know by tabulating this data, by keeping track of this data, they know, oh, these people, we can get away with charging them very little for life insurance because the chances of them dying are very, very low. So even if they're only giving us 20 bucks a month, that's all profit because we're not going to have to pay it out. Whereas somebody that's more on this end of the spectrum, they're going to be like, yeah, we have a much higher risk of having to pay out for that. So we're gonna, you know, charge them a lot more. Okay. So why are we even talking about this, right? So the reason that we're talking about this is a couple of reasons. This actually ecologically is a really good way at understanding how populations grow and understanding the composition of a population, okay? So if we take the data from this table and we turn it into a graph, that graph has a name. We call those types of graphs survivorship curves, okay? So I'm not going to show you how to do it because I don't want to, and you don't want me to because it's too much, okay? But the idea is if you take this information that is stored in this life table and you turn it into a graph, okay? You see for most organisms, one of these 3 different curves in the graph, okay? So this is what we call a type 1 survivorship curve. So a type 1 survivorship curve, number surviving is on the y-axis, age is on the x-axis, okay? So little babies, adults, okay? Middle age, right? So babies, kids, teenagers, middle age, elderly, right? So that's our age scale. And then the number of survivors, right? So this blue line, what does it tell us? It tells us, well, there's a high number of survivors in the little baby, kid, teenager, you know, young adult area. And then as you get closer to middle age and elderly, there's fewer survivors. Okay. So the punchline of this is your risk of dying is a lot higher when you're old if you are a species that has a type 1 survivorship curve. Okay. So humans have a type 1 survivorship curve, as you can see from this, right? The chance of surviving is super high until you get older, kind of towards the end of our lifespan, right? And then it goes down, right? So humans have a type 1 survivorship curve. Most large mammals have a type 1 survivorship curve. So they're showing elephants here because elephants have a type 1 survivorship curve. So most of them survive their young, their babyhood, right? In their childhood into their sort of young adulthood, right? Most of the time when an elephant dies, it's an older elephant. It's an elderly elephant that dies, okay? All right, we'll come back to type 2 in a second. Type 3 is the opposite. Type 3 is harder for a lot of people to wrap their brains around because you live in a body right? You are an organism that has a type 1 survivorship curve, so you can't fathom what the opposite is like, okay? So here's what a type 3 survivorship curve looks like. A type 3 survivorship curve means that your risk of dying is way higher when you're a little baby, right? So your chance of dying any given day is much higher when you're young. And then as you get older and older, it kind of levels out. It kind of, you know, your chance of surviving is decent. And then, you know, end of lifespan, it craps out again. Okay. So I actually don't really like the way that they show this in this particular graph. It really should be more like that instead of, it looks like everybody dies there, but it should be more like the red line that I just drew. Okay. So what kinds of critters experience this? What you're looking at here is you are looking at a larval stage of a sea star, okay? So a lot of aquatic invertebrates. I'm thinking of like sea urchins and clams and sea stars and, you know, all those guys, okay? When you're small and you're floating around in the water, life is dangerous for you, right? Because there's all kinds of critters that want to eat you, right? So your chances of surviving being a larval starfish are super low because there's 8 million different predators that want to eat you. There's, you know, rough seas that are going to, you know, move you around to wherever. So you might get moved away from where your ideal habitat is in the water. You're not very strong. You're small, right? So it's dangerous to be a baby invertebrate, okay? But if you make it to a certain size, right? So if you're this little larval starfish and you make it to young adulthood, right? Now you're strong enough that you can grab onto a rock and hold on. So it's going to be harder for predators to peel you off the rock because you're on there, dude. You're on it, right? You're also strong enough to pry your prey open and like suck their guts out. I'm telling you guys, don't sleep on a starfish, man. I mean, they're not really starfish. They're called sea stars, but whatever. Don't sleep on those suckers. You think they're all cute. They're like stone cold predators. The only reason they seem cute to you is because they're not trying to eat you. I'm just saying. Okay. Anyway, right? So they have a type 3 survivorship curve. The most dangerous part of their life is when they're young. Most of them die when they're young, right? And then once they reach a certain age, they're pretty good until, you know, until they get old. Okay. So most of their population, right, dies when they're young. Type 2, the way I like to describe type 2 is it sucks all the time, right? So a type 2 survivorship curve is when your life is basically equally dangerous no matter what age you are, okay? So a lot of small birds, well, birds in general, a lot of small mammals have this kind of situation, right? So squirrels, my favorite example is squirrel. If you're a baby squirrel, you're in a lot of danger because predators want to eat you, right? You're still in a lot of danger as an adult squirrel, right? Stuff doesn't get that much better as an adult squirrel. You're still in danger, right? So no matter what age you are as a squirrel, your chances of dying are high, equally high, right? So instead of having a curve that's shaped like that or like that, it's basically just a straight line. It's like there's no difference, okay? And whenever I use squirrels as an example, I always think about, I used to live in this little rental house. It was like a total piece of trash. Like it was a slum, man. I lived in a slum in Claremont, and location. It was all about location. And we had all these beautiful oak trees on our street, and the squirrels would run across and they would jump from one tree to the next because they would, you know, they'd kind of like arch over the road. And I remember one time I was out front, I don't know what I was doing, getting the mail or something, and I saw a squirrel beef it. He was trying to jump from one tree to the next tree, and like he missed, I don't know, and he just like bam, just like fell straight into the middle of the road, and like you could hear his little head, his little skull go like, I'm like, and I was like, oh, and I like, you know, kind of went and looked, and I was like, if a car comes, he's for sure not going to make it because then he's going to be squished. So I looked at him, and then he kind of like sat up and he kind of shook his little head. And he got up and he ran away, and I was like, all right, well, hope you learned a lesson, friend. Anyway, no matter what age you are, it's dangerous to be a squirrel. So that is type 2 survivorship, okay? So here's a little comparison. There's my squirrel, type 2 survivorship, right? And there's a lovely young lady, right, with our type 1 survivorship curve. And there's an oyster, okay? So if you don't know this about oysters, you will now. Oysters are really cool because the same thing as like starfish, they spend their early part of their life in their larval stage just floating around in the water. But once they reach a certain size, they actually cement, their shell actually forms this compound that's very much like cement, and they stick themselves to a surface. So a surface or other oysters or whatever. If they've lived long enough to get to that stage, they're pretty safe then. If they land in a good spot and they stick themselves on, okay? So that's why it's like this, super dangerous until they get old enough to stick. And once they stick, they're good until they're not, until they die, okay? So that's survivorship, okay? So the punchline with life tables is that we're not worrying about how to construct them. We just want to know, just kind of basically, that they tell you about surviving, your chances of surviving in different age intervals at different ages, okay? We use those to make survivorship curves, right? So we use that information to make survivorship curves. And understanding survivorship curves is important because if you need to know what the survivorship situation is for a species in order to understand you know, how their life works, okay? Which leads us to the last thing I'm going to talk about in this video, which is life history, okay? So there's lots of ways of living. There's lots of approaches to living, okay? And so this particular one is showing you 3 different mammals that are all pretty small, and it's kind of showing you 3 different approaches essentially, right? I like this diagram even better because it's only showing you 2, right? Showing you sort of 2 approaches. Okay, so the term life history basically describes all kinds of things. It describes what your typical lifespan is. Is it short? Is it long? It describes things like your body size. Are you small? Are you big? It describes how many babies you have. Do you have lots of babies? Do you have babies only one time? Or do you not have very many babies, but you have babies repeatedly throughout your life? Those are all topics that are enclosed within life history, okay? So all of these characteristics, fundamentally, if we look at all of those things together for any given species, what we're talking about collectively is their life history, okay? So one kind of way of living, one type of life history, is being opportunistic. So what does that mean? Opportunistic populations generally reach adulthood. Their maturation time is very short. So they reach adulthood rapidly. Remember that the definition of adulthood, when we're talking about organisms in a biological sense, is you have reached the ability to reproduce, right? So I know culturally it means something else, right? But that we're not talking about that right now, right? We're talking about you have the ability to reproduce, okay? So opportunistic populations are organisms that go from being, you know, the start of their life, being born, hatched, germinated, whatever, right? The beginning of their life, they get to sexual maturity rapidly. Okay, so you can probably think of some animals that have a reputation of that, like mice, for example, or rabbits. Okay, a lot of plants do that. Like what? So they talk about wildflowers as an example, because a wildflower, the seed germinates, and within, in some cases, even a couple of weeks, they have flowers. Well, flowers are their reproductive structures, right? And so wildflowers have incredibly short maturation times, right? They go from beginning their life to reproducing in sometimes just a couple weeks, okay? So real fast to mature. But along with that is if you go from, you know, birth to sexual maturity super rapidly, that also typically goes along with having a relatively short lifespan, right? So wildflowers only live a season, right? They don't live, it's not like an oak tree that can live 100 years, 200 years, whatever. Wildflowers live one season. Every so often they'll live 2 seasons. It's weird when they do that, but their lifespan is real short, okay? Their death rates are also usually really high, right? Most of them don't make it. They make lots of seeds, but not a lot of the seeds actually are successful. So death rates are high, okay? How many seeds do they make? Because remember, seeds are baby plants, right? How many seeds do wildflowers make? A ton, right? So every time they reproduce, they produce lots of offspring. So you're right, they're showing you a picture of a dandelion here so that you can see, look at all the seeds that are found in just one dandelion. That's potentially hundreds of baby dandelion plants. That's a lot of babies, okay? Typically though, because they make so many offspring at once, they typically only do it one time, right? So rather than having offspring multiple times over the course of their life, right? They grow up fast, have lots of babies, done, die, right? Okay. Usually they're small in size, and usually they have little to no parental care. So, you know, once the dandelion lets the seeds go, they're on their own. Okay. All right. The opposite of that is an equilibrial population. So many large mammals are this way. Okay. So I'm not looking at all of these aspects, by the way. I'm just kind of looking at the ones I'm putting dots next to because they're the most meaningful or easy to remember, I guess. Okay. So typically large mammals don't reach sexual maturity for a while. It takes a long time to become an adult, right? Relatively speaking, it's definitely not a couple weeks. Okay. Many years sometimes. Okay. Their lifespan, typically really long. So it's not a season. It's not like a wildflower, just 3 months. It might be 20 years. It might be, shoot, if we're talking about big old tree, 300 years. Okay. Bristlecone pines live so long, hundreds of years. Okay. Death rates usually pretty low. When equilibrial organisms do reproduce, they typically don't have very many at once, right? So, you don't hear about a mama elephant having a litter of 12 elephants. Such an absurd idea, right? Mama elephant has one. If mama elephant has twins, that's crazy, right? Same thing with humans. Yeah? Most of the time, the vast majority of the time, humans only have one baby at a time. I understand. 2 of you, I believe, are twins. Okay. I understand that does happen, but it is not typical, right? And even 2, we're still not talking about 12, right? And the only reason that we have situations like Octomom with her 8 babies is because, she got implanted with a truckload of embryos, right? That wouldn't happen normally. Okay. So the punchline is not very many offspring per effort. Okay. But equilibrial populations often have more reproductive events, right? So you only have one baby at a time, but then, a year or 2 later, you can have another one. A year or 2 later, you can have another one, right? So equilibrial populations can produce lots of offspring, but it's kind of spread out over time. And the reason for that is because the offspring are typically very large, right? So it takes a lot of energy to grow them. And then parental care is extensive, man, right? So whether you're talking about humans or whether you're talking about elephants, right? The young are dependent on their parents to take care of them for a really long time, right? Dandelions aren't. Okay. So those are kind of our 2 different, those are like extreme examples of life history. Okay. And so one really interesting thing might be to think about, organisms that think about your favorite animal, think about your favorite plant, right? Well, what is the life history of that organism? Are they more on the opportunistic side? Is it more on the equilibrial side? What kind of a life history does it have? Somewhere in the middle, maybe. Okay. I don't know. Right. Anyway, think about that a little bit. Okay. So that, right. So, then you can read this. Okay. So read that stuff. Right. But there's a lot of trade-offs. The strategy for which type of life history depends a lot on what kind of a organism you are. Right. So if you live in a very high risk environment, right? Maybe it's because you're a small critter, or maybe it's because of, you live in a harsh environment, right? If you have high hazard factor, high risk, tend to have shorter lifespans. Whereas organisms that live in real stable environments, right, tend to be low risk, tend to be larger, tend to have longer lifespans, right? So anyway, so this all kind of, goes like that, it all kind of goes together. Okay. All right. That's where we're going to stop for this video. One more for population ecology. And then after that, we'll eventually move on to community ecology. Okay. All right.